third talk of the memory management and analysis session is Prompt, a fast and extensible memory profiling framework. The talk will be given by Ziyang from Princeton and AWS.
Thank you for the introduction. I'm Ziyang. This work was done when I was still at Princeton. I recently graduated. Now I am working at AWS. This is a collaboration between Princeton and Northwestern University with my collaborator Yebin, Yian, Zujun, Sotiris, Simone, and David. So let's start this talk by defining what memory profiling is. So memory profiling tries to understand the dynamic behavior of memory, such as memory dependencies, points to relationship, and value patterns. With this dynamic memory behavior information, optimizations can use to optimize the program or do program analysis. Let's look at a very specific example of a piece of LVM code. So in this code snippet, you have the load and store instructions. And if we want to understand whether the store has a dependence to the load, especially in this context, whether it's a loop carrier dependence, we can look at those instructions at runtime, observing them. And when a store happens, we log this store. And when a load happens, we check if this load comes from the store. And we record it somewhere, and at the end of the program execution, we put everything into a memory dependence profile. In this profile, we record whether this store to load dependence manifested. And we can also attach additional information to this profile, in which loop, for how many times. So this is a simple example of what a memory profile is. There are different forms of them. In order to use this kind of memory profiling in your system, if you want to build analysis, optimization, there are existing ways to do that. So at the bottom of it, there are existing off-the-shelf memory profilers like SD3, LAMP, Privateer. These are memory profilers on different tasks. They are built on different systems. And if you want to build your profiler from scratch, there are also tracing tools and instrumentation tools. Instrumentation like LVM or GCC, you can just do compiler passes and just insert code and dump out the traces. So the problems of this existing approach they are usually very slow. They're not robust. If you go outside your defined case, they sometimes crash. They're hard to develop. They're hard to adapt. I'll get into some of the detailed problems later. But as a result, this blocks the adoption of clients like speculative automatic parallelization, which is a topic that our research group have been working on for a long time. So with all these, let's get down to a little bit more details. What are the challenges? So we saw those problems. So what are the challenges that made those problems appear? What are challenges in developing practical memory profiler? The first challenge of developing a memory profiler is the profiling overhead. So if we look at this code snippet before, we are observing those load and stores. So essentially, we need to report it to somewhere. So naturally, there are two kinds of overhead. One is associated with the instrumentation, which every time you do a load and store, you need to take extra cycles to do this load and to report this load and store. This can be several times to several hundreds times more expensive than the load and store itself. And then there is analysis overhead. Then after you record all these events, you need to do analysis to summarize it into profiles. And that can be several to 1,000 times compared to the load and store instruction itself. So this overhead is very high because the simple fact that load and store instructions, this kind of memory instruction, are very high throughput. You have billions of load and store memory instructions per cycle. Roughly 1 out of 5 instructions on x86 are memory instructions. These are much more than the function events, call, return, that people are used to, and use that to do hot call stack execution, flame graph, those sort of things. So that means like memory profiling is essentially have a higher throughput to deal with. And sampling is used like widely for even functional profiling. However, for important clients like speculative parallelization, it just doesn't work that well. Quote from a paper, the difference in accuracy has a considerable impact on effectiveness of the speculative optimization performed. So we do want very accurate and precise profiling results. So for many clients, we cannot resort to sampling to do this speed up. The second challenge is to implement such memory profiler. You essentially need to understand compiler or tracer to understand how to instrument it. And you need to have system programming knowledge to write it up. And throughout the framework, you need to think about how to optimize it through parallelism and using compiler optimization. So there's a knowledge requirement. And the third piece of the challenge is the implementation complexity. Let's take two existing memory profiler. There are thousands of lines of code for each of this profiler. Sometimes you need a couple to support your client. This couple thousand lines of code doesn't seem too much, but consider that changing it, like adding more functionality, needs all those prior requirements, and this is just the first step for putting your larger system. Then it all come together, there's a high complexity of implementation. With all these challenges, I beg the question, is it even possible to build fast and robust memory profiler with ease? So to answer that, I looked at all the existing memory profiler that I mentioned and think about what are the opportunities to improve it. The first insight is actually the generalization opportunities around. So there are a lot of things that all these profilers did that they implement their own way, but they can be shared. For example, the instrumentation, when you try to add those additional instructions, why can't we share those components? And the profiling logic, data structures, and optimizations that people do to remove unused instrumentation, to do parallelism, why can't we share all those? So the first insight over here is to generalize all these components and optimizations that people have developed for memory profiling. The second insight is if we look at this memory profiling, there's one aspect of latency and another aspect of throughput. Latency is defined as from the time that a memory event happened to the time that gets summarized into a profile. So this latency actually doesn't matter because you only wait till the end to look at the profile. But the throughput, how fast you can ingest and process those events is very important. We have very high throughput requirements and no latency requirements in this case. Based on those insights, I present to you the prompt framework, a fast and extensible memory profiling framework. We picked the name before large language model got popular, and we have a redefinition of what prompt means. But yeah, it means fast. And you don't need to like read all this text over here. All I want to highlight is with prompt, if you want to implement a new memory profiler, you only need to implement the core logic. So from the previous graph, you see that like on a high level, we broke it down into two pieces. There's a profiling front end that generates all the events, and there's a back end that processes all those events. So the benefit of decoupling this is first to reduce the profiling logic complexity. Now all the logic of processing these events goes to the back end. And it also minimizes the interference between the profiler and the program under profiling. Now they're running on two different processes. And on the performance benefit, we are seeing pipeline parallelism. You have two processes working for generating profile. And this is the first sign of trading latency for throughput, the insight we had earlier. Going to front end of the profiler, the thing we did in the front end to generalize it is to standardize all the profiling events that people use in their profilers and allow people to express what they want in a YAML format, it's implementation details. But essentially, we map all the events and the information you want to this format. So prompt will actually do instrumentation for you. And over here, we remove those unused instrumentation. When you specify those ones you need, those unused ones will get automatically removed at link time through some link time optimization. For the back end of the profiler, we provide a bunch of components that help you to implement your memory profiler. That includes a shadow memory that tracks metadata of memory addresses, context manager, data structure with insertion logic, and some optimization, a data parallelism wrapper. So it's easier for you to implement those memory profilers. So I want to dive into two more details to show how we use this trade latency for throughput throughout the system. First, when we have a bunch of dependencies, that memory dependencies generated, we want to summarize into how many times dependence happens. It's essentially insertion logic. You're inserting these dependencies into a data structure. And to improve the performance of that, we add a buffer. Now with a buffer, you're not inserting to a hash map. You're inserting to a vector, which is fast. And when the buffer is full, we do map reduce, reduce that into the complete map. So by adding a buffer here, we trade latency for throughput and improve the performance. You can look at those details in the paper. And another, with a very similar insight, remember we have the profiling front end and back end. They're communicating all the events throughout a queue. And to improve that, we use double buffering or ping pong buffer. So there's a buffer associated with the back end. There's a buffer associated with the front end. And they're processing independently and then swap buffers when they finish processing. It's a classic double buffering design. Again, trade latency for throughput. We can compare those performance numbers with prior queue design. So yeah, putting them together, we have a fast extensible memory profiling framework. Looking at some evaluation result, first, it's extensible, so we save the lines of code you need to write. We re-implement 2 memory profilers with prompt framework. And the conclusion is we reduce more than 60% of lines code in the implementation. And for the performance aspect, we compare to those 2 profilers. And we see, the performance improved by 80% reduction in the profiling overhead. But what it actually gives you is actually a different way of thinking about memory profiling. Instead of having monolithic profiler that does everything and very complex design, now we can think about what the client requires. So we go back to one of our prior work on automatic parallelization and look at all the profiling needs this work needs. It can boil down to 4 new profilers implemented with a profiler with 570 lines of code. It works on more benchmarks. And comparing, when evaluating on the exact benchmark that were in the original perspective paper, we drastically reduce the overhead of the memory profiling. The key takeaway here is by redesigning the memory profiling workflow with generalization of components and optimization, trade latency for throughput, prompt achieve performance and extensibility, significantly reduce implementation effort, and unblocks clients like speculative automatic parallelization. Prompt is sitting in this bottom of the stack, collaborating with other components of the parallelizing compiler stack. And thank you. That's all.
Questions?
I have a question. So you said that there was a 60% reduction in the amount of code that you had to write to make this specific to the different re-implementations that you did, for examples. So what did the leftover 40% wind up being? Because you said that you basically configured it through a JSON file. So was it just a 1,000-line JSON file? Like, what was the code?
Thank you. That's a great question. So if we look at the two profilers, we'll break it down by different parts. And the most of the leftover logic, like for LAMP, is the core profiling logic. So the LAMP is a pretty complex memory profiler. It's loop aware. So it's doing different stuff when a loop is in different state. So there's a complex core profiling logic for that. So when we were porting this existing memory profiler into our system, this still requires some effort, but now it's focused on the profiling logic part. So when we looking at the client again, that's a later part of the work that we reduced, that we understood what exactly those clients need in terms of profiling. We can redesign our profiler to only use a very small portion of the core logic, and that's when we see with several hundred lines of code, we can satisfy all the need of the client. Yeah, so for this part, mostly the profiling logic is taking a lot of lines.
So you basically allow the core profiling logic to be extended and then replace, or somehow you how do you expose the API that enables you to make it specific, I guess is? It
really depends on why. So I guess the question boils down to why are the existing profilers so complex? Why they require so many codes in their core profiling logic, where in another case, when you implement for those specific needs, you only require several hundred lines of code.
It's more like I'm helping. Well, okay. My research is more like I'm making an instrumentation framework, so I'm interested from the perspective of an instrumentation framework creator.
Okay.
How do you create something that's generic and customizable to specific use cases? So how do you expose that functionality?
Yes. For the instrumentation part, it's quite easy. You express the YAML file. We essentially replace it with prompt. And you express what you want, the information you want, and prompt will actually do the instrumentation for you and remove unnecessary ones.
Any other questions?
I was just wondering about multi-threaded support. I think you mentioned in the paper that you don't support it, but could you say a few more words about it?
Yes. So that's a great question, everyone. We are trying to parallelize code. Why is the profiler itself doesn't support multi-threaded? Yes. So the current implementation does not support multi-threaded profiling. But by decoupling the memory profiling into the front end and back end connected with the queue, we actually make it possible when with different threads or processes to generate to the same queue. The order might be tricky in that case. So the better reason for this specific work to not include it is it was very much inspired by parallelizing the code. So we have sequential program as an input, then we try to parallelize it. So that's why we didn't have it. Yep.
I was kind of assuming that you want to profile the result after the parallelization as well.
That's a great point, yes.
Thank you, Ziyang.
Thank you.